Welcome to The Explainer. Today, we're going to talk about something pretty incredible, the engine inside you that switches from feast mode to famine mode, sometimes all in the course of a single day. I mean, think about it. This cycle is absolutely fundamental to our survival, something we've perfected over millions of years. It's this precisely choreographed dance between storing energy when you've got a ton of it and then releasing it when you don't. So how in the world does our body pull off this constant, critical balancing act? Well, the best way to think about it is like a super sophisticated hybrid engine, right? It's not just burning one type of fuel all the time. Instead, it's constantly adapting, constantly recalibrating, all based on one really simple fact: have you eaten recently or not? In this whole process, it's controlled by two dueling hormones that have this perfect back and forth relationship. When one is high, the other is low, no exceptions. Right after you eat in the fed state, insulin is the boss. Think of it as the storage manager, telling your body to pack away all that energy. But in the fasting state, a different hormone, glucagon, takes over as the release manager. Its job is to find and create fuel to keep the lights on. All right, let's start with the fed state, those few hours right after a meal, when your system is just flooded with nutrients, and the number one priority is, saving for a rainy day. Okay, so it all kicks off with step one. The carbs from your lunch hit your bloodstream and your blood glucose levels shoot up. That spike is the signal for step two. Your pancreas releases our storage manager, insulin. And that brings us to step three. Insulin gets right to work, basically shouting instructions to your liver and muscles to pull all that extra glucose out of the blood and pack it away as this dense energy reserve called glycogen.
This is a time of plenty, The body isn't just storing energy. It's also in full-on growth and repair mode. Every tissue is taking exactly what it needs for right now and then diligently saving the rest. The whole system is just designed to capitalize on that abundance. Now, let's fast forward a few hours. The fuel from that meal has been used up or stored away, and your body just smoothly transitions into the fasting state. So as your blood sugar levels start to dip, insulin just quiets down, and the pancreas sends out glucagon. Now, glucagon's mission is the exact opposite of insulin's. It has to find and literally create fuel to keep your blood glucose stable, especially for your brain, which is a huge energy hog, and importantly, can't use fat for energy. So, where does this emergency fuel come from? Well, the liver becomes the hero of the story. It fires up this amazing process called gluconeogenesis. The name says it all: gluco for glucose, neo for new, and genesis for creation. The liver is literally making brand new glucose from scratch. But where does the liver get the raw materials to do this? This is the really clever part. It just recycles byproducts from other tissues. The main ingredients are lactate from your muscles, the amino acid alanine, also from muscle, and glycerol, which is basically the backbone of fat molecules that get released from your fat tissue. And get this, what's truly remarkable is that over 90% of all the new glucose your body makes while fasting comes from just these few key sources. This is not some random scramble for fuel. It is a highly efficient, targeted recycling program that evolution has perfected. And the body uses these really elegant recycling systems to shuttle all these materials back to the liver. The Cori cycle is a simple loop. Muscle makes lactate, the liver turns it back into glucose and sends it on back. But the Cahill cycle, it's even more sophisticated. It uses alanine not only to carry building blocks for glucose, but at the same time, it carries toxic ammonia safely away from the muscle to the liver so it can be disposed of. Just brilliant. So we've seen this beautifully balanced system in action, but its intricate design is also what makes it kind of fragile. And to really appreciate the genius of this engine, it actually helps to see what happens when just one tiny cog in the machine fails. Okay, this may sound bizarre, but it's a classic clinical sign of a rare disorder called alkaptonuria. It's the perfect illustration of our point. A single broken enzyme in a really long metabolic chain means a specific substance can't be processed. So it builds up, it gets excreted, and then it turns black when it's exposed to air. One tiny fault leads to a completely different, very strange output. And this really shows you how understanding these pathways is kind of like being a detective. Take two diseases, Tay-Sachs and Niemann-Pick. They look almost identical. Both cause awful neurodegeneration and a characteristic cherry red spot in the eye. But there's one subtle difference. Niemann-Pick causes an enlarged liver and spleen, that's called hepatosplenomegaly, while Tay-Sachs does not. That one single clue is often enough to pinpoint the exact problem. To keep track of all these subtle but absolutely critical differences, doctors and students use these clever little memory aids. For Pompe disease, which uniquely damages the heart, the phrase is, Pompe trashes the pump. For Hunter syndrome, where vision is spared unlike in a similar disease, it's hunters can see. They're just simple tools for quickly connecting a pattern to its cause. And we see the same exact detective work with vitamin deficiencies. A lack of either B12 or folate leads to the same type of anemia. But then the trail splits. Only B12 deficiency causes neurological damage and a buildup of a specific compound in the blood called methylmalonic acid. That substance acts like a crystal clear chemical fingerprint, telling doctors exactly which pathway is broken.
So, after seeing how the system works in both feast and famine, and seeing how it can break down, what's the big takeaway from all of this?
Well, the most important lesson here isn't to get lost in the weeds. You really don't need to memorize the entire complicated metabolic subway map. The real power comes from understanding the bigger picture.
Instead, that power comes from understanding the touch points. What are the key regulatory enzymes? What are the hormonal signals, like insulin and glucagon, that turn things on and off? And what are the clinical consequences when things go wrong? Grasping these things gives you a real functional mastery of the system.
And all this leaves us with a final, kind of provocative thought. This incredibly efficient engine, designed to cycle between abundance and scarcity, now operates in a world where, for many of us, it's always the fed state. So how does this ancient machinery, perfected for one environment, adapt or maybe fail to adapt to our modern world of constant feasting? That's a question that is absolutely central to so many of today's health challenges.